So for another example of where we can use a proof by contradiction, consider the following. Say we want to prove that the square root of 2 is irrational. So you may or may not have seen the definition of what it means to be a rational number or irrational number. So just for completeness sake, let's go ahead and define that. A real number x is called rational if you have two integers a and b such that you can express x as a ratio of a over b. And if you can't do this, we call that number irrational. And it's called irrational otherwise. And so irrational, so if you can't do this, that means that you cannot find integers a and b such that x is expressed as a ratio of a and b. So what we want to do is show that the square root of 2 is irrational, that it cannot be expressed as the ratio of two integers. First off though, a little bit of an aside, because a lot of the proofs that we've been proving so far have been very mathy and theoretical, or you could consider them somewhat simple, you know, n is even, if and only if n squared is even, etc. So what in the world does all this have to do with computer science? So why is it important to show the existence of irrational numbers? So if we show the square root of 2 is irrational, we would show that there are irrational numbers. Well, it turns out the case that this is really important because note, all the floating point numbers that you work with, they are all rational numbers. They're all rational. And so if you run into an irrational number, you're going to have a hard time because you can't represent it with a floating point number. And why is this the case? Why are all floating point numbers rational? Well, if you actually take a look at the specification for a floating point number, we have that our IEEE 754 specification of what it means to be a floating point number is as follows. You have a plus or a minus, and for that you get to devote 1 bit to it. And then you multiply that by what's referred to as the significand, and then you multiply that by some base to an exponent. So basically it's like scientific notation. With this specification right here, this base has to either be 2 or 10. And then you get to choose how many different bits you get to devote to your significand and your exponent. So if you're operating on a computer with, say, 64 bits, well, you know, one of those bits has to be devoted to the sign, and then you get to choose how many bits that you get to devote to the significand and the exponent. So let's say, for example, you are working on a 64-bit machine. And let's say that you want to be really, really accurate. And so you're going to devote 31 bits to your exponent. So let's go ahead and choose a base of 10. And then I'm going to devote 31 bits to my exponent. And I'm going to make my exponent, just as an example, let's make it -8. 31 bits for that. And then I want to multiply this by some significand. So I'm going to pick a special significand, and it is going to be 314159265. And this is going to be my significand. And so it actually turns out that to represent this number here in binary, it takes 30 bits to represent that number, and it's a positive number. So if I have a plus out front here, I have 1 bit to say that this is a positive number. So you can see how I've go ahead and distributed my 64 bits. I devoted 31 of them to my exponent and 30 of them to my significand. So this is a floating point number, and this is a -8, so you can see that this is the first few digits of pi, right? 3.14159265, yada, 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 like that. Well, this is a floating point number. We only had a finite number of bits to work with, and so actually, if you took this expression right here, and if we rewrote this times 10 to the -8, since this is a negative exponent, that means we put it in the denominator. This number right here is equal to the following. So we have that this number is an integer over an integer. Well, that was the definition of a rational number. And indeed, any sort of example like this, if it's a floating point number, it's a rational number. So there is no way using floating point numbers you can express an irrational number. So then, how, as a computer scientist, do you deal with irrational numbers? Because a curious math fact is actually that there are way more irrational numbers than there are rational numbers. You can make that concrete. It actually turns out that almost every real number is irrational. So there's lots of them out there. Ask me sometime about how computers actually deal with irrational numbers, because if you've ever dealt with a computer algebra system like Mathematica or Maple or one of these sort of systems, you'll notice that you can actually operate on irrational numbers with a computer, but they do it in a very special way. They do not use floating point numbers to represent it if you want to properly deal with irrational numbers. So even though this seems like a very mathy kind of example right here, and sort of abstract, it has application because every single floating point number that you're dealing with can't represent irrational numbers. So it's pretty important to know that those things exist.